All right, so last time we talked about the virial equation as a way of summarizing the behavior of real gases. And so it's a convenient way of summarizing the behavior of gases. Basically, what you do is you fit an isotherm, okay, to an equation that says Z, that expresses Z, the compression factor, in terms of the pressure or the molar volume. So in this case, you have 1 plus a constant times the pressure plus another constant times the square of the pressure and so on. This B prime right here is called your second virial coefficient. Okay. And so if you have that data, if you were, let's say you have that for a particular temperature. Okay, so you have those values for B prime and C prime. What happens if you take the derivative of Z with respect to pressure at constant temperature? So this subscript over here means constant temperature. Then that's going to be equal to what? Derivative of a constant is 0, right? So it's just going to be B prime plus 2C prime P. What will be the next term? You're going to have a D prime P cubed over here. So the next term here is going to be 3D prime P squared and so on. What happens if you take the limit of that as temperature approaches 0? What happens to your virial coefficient? As as pressure approaches 0. That's a typo right there. As pressure approaches 0. So this all these extra terms will drop out, right? So the limit will just be equal to B prime. So that, what does that mean? If you have a plot of Z versus pressure, okay, what did we say the ideal plot looks like? Z is equal to 1. It's just constant, right? What would the real plot look like typically? Below the critical temperature, it's going to dip and then go up, right? So if you were just to eyeball that graph, that plot, how would you determine B prime? It's the limit of the derivative of Z with respect to P as pressure approaches 0. What's the derivative of Z with respect to P? What's the geometric interpretation of that? The slope of the tangent line to your curve. So the tangent line as you're approaching 0 would be that, right? So that slope. So in this particular case, then what do you expect B prime to be? Positive or negative? Okay, so here you have B prime is going to be less than 0, right? That's the derivative of Z with respect to pressure, okay, as the limit of that as pressure approaches 0. Okay, so the observed trend in B prime values is it's negative at low temperatures and eventually it becomes positive at high temperatures. So you have a series of isotherms. Low temperature isotherms would have a negative B prime, and high temperature isotherms, very high temperatures, your isotherms would have a positive B prime. Okay, so a negative B prime simply means that your Z drops below 1 before it rises. The more negative the B prime is at a given temperature, okay, that means it dips more, right? And the interpretation of that at the molecular level is you have stronger intermolecular forces. All right. Now you could actually relate the second virial coefficient. Remember, this B is related to B prime. What was the relationship between B and B prime? You remember? Let's see. You were able to relate B and B prime earlier. Here. B is B prime times RT, right? So what's the difference between B and B prime? If you were to plot Z versus P, okay, if you're expressing it in terms of pressure, then your second virial coefficient is B prime, right? If you're using molar volume, then B times 1 over molar volume plus C times 1 over molar volume squared. That's your second virial coefficient. We say B here is equal to B prime times RT, right? So B and B prime are called the second virial coefficients. It just depends on what what your independent variable is, if you're using pressure or concentration. Concentration being 1 over the molar volume. Okay. Now, for a van der Waals gas, for a gas that obeys the van der Waals equation, you can show that your B, second virial coefficient, can be expressed in terms of the van der Waals parameters B and A. Okay, so it's B minus A over RT. What did we say B was, the little small b in the van der Waals equation? What does it account for? It accounts for the size of the molecules, right? So it accounts for the fact that molecules can only get so close before repulsion starts to predominate over the attractive forces, and you can only get those molecules so close before they start repelling. And what does the van der Waals parameter A account for? No, that's excluded volume. That's B. B is excluded volume. That's due to repulsion. A accounts for attractions. Okay, and that tells you how that's related to how much that thing dips, how your Z versus P dips below 1, right? That's related to that. So, and you can see why that's the case right here, right? So your second virial coefficient, you can see, is just directly proportional to B is just directly proportional to B prime. The higher the B prime, the higher the B, right? So if B prime is negative, B is also negative. All right, so let's look at this. B minus A over RT. What happens at low temperature? What happens if this T is a very small number? So your denominator here is going to be small denominator, right?
Is that just the A under the RT, or is that B minus A?
Okay, then let me rewrite that for you. This is B minus A over RT. Okay, so if your temperature is very low, what happens? Very small denominator, this term becomes large compared to B, right? So your attractive term is important. So attractive forces are important, okay, when dealing with low temperatures. What happens at high temperatures? That's gonna, so your B approaches, big B approaches little b, right? So if at very high temperatures, this term will drop out. So at very high temperature, then you say that deviations from ideal gas behavior is primarily going to be due to repulsions. At the molecular level, we interpret this as that at very high temperatures, these molecules have very high energies. Okay, so attractive forces tend to be irrelevant. What would cause any deviation from ideal gas behavior is just they just can't get close enough before because of the repulsion. So it's the deviations from ideal behavior is going to be primarily due to repulsions. But at low temperatures, okay, they may not have enough energy to overcome those forces of attractions between them, and so that the attractive term in your van der Waals equation becomes important. Okay. Now, there's a temperature where you get a balance of forces between attractive and repulsive forces. Okay, and that is known as the Boyle temperature. So the Boyle temperature is when this second virial coefficient is equal to 0. So if we set this thing equal to 0, how do we solve for the Boyle temperature? That will just give you T. B equals A over RT, right? And you can say that you can solve, and this time your temperature is now your Boyle temperature. Solve for Boyle temperature, you get Boyle temperature is equal to A over PR. That B and R in the denominator, okay? So at the Boyle temperature, we say your gas behaves ideally over an extended pressure range. So if you look at your Z versus P plot, okay, At low temperatures, it tends to dip, right? At the boil temperature, it dips below Z equals 1. At your boil temperature, over an extended period, extended pressure range, your gas is behaving ideally. Z is very close to 1. And then at very high temperatures, what happens? You have a positive second Virial coefficient. Okay, so this is your high T, this is your low T, and this one is you have your boil temperature right here. And so let's see, what would a plot of the second Virial coefficient versus argon look like? What happens? What's the value of the second Virial coefficient at low temperatures? It's going to be negative, right? So it's going to start out negative, and then what happens? It's B minus A over RT. So as T approaches infinity, what happens to your value of B? It approaches the value of little b, right? Asymptotically. So that is a plot of B versus T for argon. Where would you find this? You look up a table of van der Waals parameters. There should be one in your textbook. Okay? And you can calculate, you should also be able to calculate that from the critical point data. Remember? How do you calculate the van der Waals parameters from critical point data? Earlier slides. Let's see. Right here. Okay. So from your critical temperature and critical pressure, you can calculate the van der Waals parameter A and the van der Waals parameter B. Let's talk now about the law of corresponding states. This is a general observation, empirical observation, that properties of gases are the same if we compare them to the same conditions relative to the critical point. The value of this is it simplifies the tabulation of the data for gases, because you cannot just put Z versus P data at every temperature for every gas in a table, right? So you're going to have a very, very huge publishing task there to get all of that information. And so what we actually try to do is we summarize everything in terms of your virial coefficients. So if you tabulate the virial coefficients, then that narrows that. You can just use those virial coefficients to calculate your Z. Now, even those virial coefficients, they do depend on temperature. So those B prime, the C prime, and T and D prime, and so on, those are all also expressed as a polynomial in temperature. So you can have them expressed in terms of temperature. So if you know the temperature, you can just calculate those rather than looking at a table of B values at different temperatures. Typically, if you look it up from a handbook, you'll just find an equation that allows you to calculate for those virial coefficients if you just plug in the temperature. Okay, so that's just a convenient way of summarizing information. The nice thing about gases is that if you were to compare them at the same conditions relative to the critical point, most gases will behave the same way. Okay? So in order to specify what we call conditions relative to the critical point, we calculate what are known as reduced variables. So what's a reduced variable? Well, the reduced temperature is simply the ratio of the temperature to the critical temperature. So what's the unit for reduced temperature then? Unitless, right? Reduced pressure is just the ratio of the pressure to the critical pressure. And the reduced volume is just the molar volume divided by the critical volume, the molar volume at the critical point. So those are reduced variables. So if you have two gases that have the same reduced variables, they're going to have the same Z. That's what we're saying here. Okay? So another way of stating this is to say two gases that have the same reduced variables, value for their reduced variables will have the same Z. Okay. So here's a plot that illustrates the law of corresponding states, or the principle of corresponding states. It's kind of hard to see, huh? So here is a plot of Z versus reduced pressure. Okay? Notice that the gases plotted here are nitrogen, methane, propane, and that's ethene. Okay? So look at all those data points. For a given isotherm, this is when the reduced temperature is 1.0, this is what it looks like. This is at the critical point. Okay? All the points fall more or less on the same line. When T sub r equals 1.2 right here, okay, you can see the data points fall on the same curve. So we say that two gases are in corresponding states if they have the same Z. So at the same reduced pressure and reduced temperature, you would expect two gases to have the same Z. Of course, there are exceptions, but this is a very good tool for us, especially for predicting things. Okay, so here's a question: how would you determine the state of gas A that corresponds gas B that corresponds to gas A at pressure PA and TA? So here's gas A, okay, and the pressure is P sub A and T sub A. What sample of gas B would have the same would have the same corresponding state? Well, what you do is you look up PC and TC for gas A, the critical point for gas A. Okay, so what do? You calculate from here. So you look up PC and TC for gas A, and so your reduced pressure is going to be equal to PA over PC of A, right? Critical pressure of A, and the reduced temperature is just the temperature of gas A divided by its critical temperature. Right? So what would be the corresponding state for gas B? So what is PB and TB that corresponds to PA and TA? Then you would say if they're in corresponding states, then they must have the same TR and PR. So that means this must be equal to the corresponding state, the corresponding pressure for gas B divided by the critical pressure for gas B. So you'd have to look up the critical pressure for gas B. And this must be equal to temperature of gas B divided by the critical temperature of gas B. Okay? So how do I solve for PB and TB? I just use this equation right here, right? Solve for the pressure of B that corresponds to P sub A. That's how you would figure it out. So, and solve for the temperature of B that would correspond to T sub A for gas A. Once you know PB and TB, then these two gas samples are going to have the same Z. Right? Let's see. Now, if you were to go to the van der Waals equation and actually did a substitution, okay, if you were to express your pressure, volume, and your temperature in terms of the reduced variables, okay, this is the equation you end up with. And what do you notice about this equation for the van der Waals equation? The A and B are gone. Okay, so that sort of justifies the principle of corresponding states. At the same PR, VR, and TR, you have, as for the same reduced variables, it doesn't matter what gas you have. Okay, gases have the same properties at corresponding states. They have the same compression factor. It doesn't matter. You'll notice here in the expression for the van der Waals equation in terms of reduced variables that the A and the B. These are the things that depend on the nature of the gas, right? They disappear. So that's a very useful equation to use because you don't have to worry about what kind of gas you're dealing with. And in fact, in terms of reduced variables, you can show that the compression factor is just equal to the reduced volume divided by reduced volume minus 1/3 minus 9 over 8 times reduced volume times reduced temperature for a van der Waals gas. And again, you can see, okay, they all have the same Z. It doesn't matter what A and B are. If two gases obey the van der Waals equation, at corresponding states, those two samples of gases will have the same Z. All right. So what's the value of Z at the critical point? Experimentally, you'll find that Z at the critical point is fairly constant, anywhere between from 0.26 to 0.30. Again, an illustration of the principle of corresponding states. You can see it's not exactly just one number. So helium, for example, is 0.30443. C6H6 as benzene, you'll have a value of 0.26724. Okay. Now, if you were to calculate this, the Z for a van der Waals gas, from the van der Waals equation, you'll find that the prediction of the van der Waals equation is that it's going to be 0.375. So you can see it's not really very accurate. Okay? For very, very accurate work, you really should not rely on the van der Waals equation. It's a nice equation for us to use because it gives us insight into the molecular reasons for deviations from ideal behavior, but it's not a perfect equation. It doesn't completely account for everything. Okay, the Redlich-Kwong equation will give you a Z value of about 0.333. As I mentioned earlier, a Redlich-Kwong equation is another two-parameter equation. It's similar to van der Waals equation, and it's just a little bit better than the van der Waals equation. Okay. But if you really want highly accurate calculations, the best thing to do is go to the Virial equations because those are based on empirical data. Those were intended to fit actual experimental data. All right. So here's an application. What's the molar volume of gas A at pressure PA and TA? All right. If you were doing this in freshman chemistry, how would you solve for this problem? Molar volume means volume divided by number of moles, and you would have just said what? Since PV equals nRT, RT over P, right? That's true if the gas were behaving ideally. In general, the number you get there is not going to be correct, especially when you're dealing with very high pressures. So if you have, for example, a gas sample, a tank of helium at very high pressure, a tank of argon at very high pressure, this formula is not going to work. So what would you need to do to answer this question? You'd have to look up the critical pressure and the critical temperature of gas A. So you refer to a table, look up that value, the value of the critical pressure and the critical temperature. And then what do you need to do now? What you need to do now is calculate the reduced pressure and the reduced temperature. How do we do that? We know what PA is and what TA is. So what's the reduced pressure? PA over PC, and the reduced temperature is TA over TC. Then you go to a chart of Z versus reduced pressures at different reduced temperatures and estimate the Z from there. So you remember that chart I showed you earlier? Okay, let's go back to that chart. You'll find charts like those in handbooks. Okay, so a chart like this. So you locate your PR. Let's say your PR is, let's say, a reduced pressure of 2. Okay, this is your PR, reduced pressure of 2, and let's say your reduced temperature is 1.2. So this is the reduced temperature isotherm of 1.2. So you locate that point. So you calculate your PR and TR. You refer to a handbook that has a series of all these curves. So you look for the curve corresponding to the reduced temperature you're interested in. Let's say your reduced temperature, for example, is 1.2. Then you look for this curve right here. You locate your PR, and then what do? You can look up what Z is. So let's say, what's our Z here? You get a Z of about 0.6. Okay? So that means your volume would be about 0.6 times the ideal volume. Remember, Z is the ratio of what? The volume to the ideal volume, right? So the idea here is, if you know your reduced pressure, you know your reduced temperature, you refer to a chart to figure out what the Z is for that gas. If you know the Z, then you just multiply the ideal volume by that Z, and you get the real volume, the actual volume you'd find in a real-world sample. Okay? So here's an example. What's the molar volume of argon at 181 Kelvin and 96 atmospheres? PC and TC of argon, you can look it up. You'll find the critical pressure is at 48 atmosphere and the critical temperature is 150.72 Kelvin. All right, first of all, that's the ideal volume. Ideal molar volume. RT over P, right? So what's RT over P? What's our R? Since we're dealing with atmosphere and Kelvin, what value of R do we use? 0.08206 liter atmosphere per mole per Kelvin. Our temperature is 150.72 Kelvin. Okay, I need more room here. Liter times atmosphere per mole per Kelvin times 150.72.
That's the critical.
Oh, I'm sorry. The temperature our temperature is 181 Kelvin. Okay, divided by 96 atmospheres. That's our pressure. So what's our ideal volume?
Uh,
0.155 liters. Okay. Liters per mole. Right? Temperature, Kelvin cancels out, atmosphere cancels out. RT over P is ideal volume, molar volume. Right? Ideal molar volume. What's our expected Z? First of all, what's our reduced pressure? How do we calculate reduced pressure? The actual pressure divided by critical pressure, which is 48. So 96 divided by 48. How much is that?
it's 96.
Oh, 96 over 48. 96 over 48. So that's 2.0. 2.6. What's our reduced temperature? 181 Kelvin divided by 150.72. 1.20. Okay. So you look at your chart. You look for the isotherm with the reduced temperature of 1.2, and this is the 1.2 isotherm right here. Okay. So what do you do now? Locate on that chart our reduced pressure, which was 2, right? So reduced pressure of 2, and that's your reduced temperature. So estimate What's our Z at that point? Close to 0.6, right? Not quite 0.6, maybe 0.5, 5859, right? So let's just say 0.58. So you're going to say Z, according to your chart, is 0.58. So what is our real molar volume? Is time Z times the ideal molar volume. So it's going to be 58% of the ideal value, which is 0.155 liters per mole. So that gives you 0.0899 liters. So 0.090 liters, right? So it's smaller than what it should be. It occupies a smaller volume than what it should. And so how do you account for that deviation from ideal behavior? What's at the molecular level, what happened? You have attractive forces uh, keeping those molecules closer together, as opposed to the ideal case where they just ignore each other. Okay? So, let's see. Let me show you an animation that summarizes the interaction between two gas molecules. You can go to a website called phet.colorado.edu and you look for atomic interactions. This one right here. So here's a potential energy diagram for that summarizes the interaction between a pair of atoms. This one, let's just do argon and argon, okay? And you'll notice what happens to the potential energy at very large distance. It approaches a constant value. It's flat. What does that mean? That means minimal interaction between the two atoms, right? So what would happen then if I were to if the atoms were to approach each other? Eventually, what happens? The potential energy is going to drop, right? So since the energy remains constant, if potential energy is dropping, what's happening to the kinetic energy? It's going to be increasing. They're going to speed up, right? So here you have speeding up. You get as your potential energy drops, the difference between the total energy and the potential energy would be kinetic energy. So they'd be speeding up as they approach. And where would they reach maximum speed? Where you have at the minimum of your potential energy, you get maximum kinetic energy at this distance, right? So what would make them speed up as they approach? Attractive forces. So you can see this dip in your potential, okay, is due to attractive forces. What happens once you're past this minimum right here? Repulsions start to predominate over attractions. Eventually, they slow down. Eventually, they stop, right? And when they stop, so if this was the total energy, okay, constant speed, speed up a little bit, speed up some more, maximum speed, slow down, and then they'll stop when they hit that point right there, right? So if I were, so let me start the animation at the point where they have stopped. Let's say this is the total energy, and so they've approached each other as close as possible. So this is as close as oops, sorry. Turn the atom. Okay. Okay. So they're as very close together now. The repulsion is really strong. What happens? They're just going to separate, never to see each other again. Okay? But what if, so that would be the average relative kinetic energy of the atoms at high temperature, right? But what happens if you cool down your gas sample? The average relative kinetic energy would be very low. So what happens if your average kinetic energy is just down here? The average total energy is just down there. Then what you'll have, okay, be, let's see if they don't, at very low temperatures, the total energy is low. It's going to stay down there. Okay, so you have your total energy is just there. So you're actually able to form a diatomic argon molecule. Okay, so at very low temperatures, you can have a diatomic argon. You can have diatomic argon molecules. And so if you were to examine this in terms of the ideal gas equation, PV equals nRT, okay, a pair of argons will now behave as though it's just one gas molecule, right? Rather than one gas particle, rather than two gas particles. So if you look at PV equals nRT, your effective number of moles, you can think of the effective number of moles as lower, right? So the pressure that your gas would exert is lower than it would be if it was behaving like a collection of individual argon molecules behaving ideally. So if pressure is less than ideal, what would your Z be? It would be less than 1. Okay. What happens at very high temperatures? If the temperature is way up here, okay, then these tend to be, the well depth here tends to be very, very shallow, okay, compared to like at room temperature, the average energy of argon atoms at room temperature will be way up here. This is around 0.01 electron volts, okay. This well depth right here is around 0.01 electron volts for argon, a pair of argon atoms. Okay, that epsilon right there. What's the average kinetic energy of argon atoms at room temperature? 3/2 RT. Okay. 3/2 RT. And what did we say RT was? R is 8.314. Temperature is 298 Kelvin. This is joules per mole per Kelvin. Calculate that. So R equals 8.314. .314 joule per mole per Kelvin. Okay, temperature, let's say 298 Kelvin. So R times T equals that many joules per mole. Okay, 2.5 kilojoules per mole, remember? RT at room temperature. Okay, how about what would be the actual, on a per molecule basis, what would that be? So R times T divided by Avogadro's number. 6.022 times 10 to the 23rd. So that's a small number. Change our zero tolerance here. Okay, this is to make my units consistent, molecules per mole. So 4.1 times 10 to the negative 21. What's that in electron volts? 4.1 times 10 to the negative 21 divided by 1.6 times 10 to the negative 19 joules per electron volts per joule. Joules per electron volts. That's about 0.03 electron volts. Okay. Oh yeah, times 3/2. I'm just getting orders of magnitude. So if you multiply that by 1.5, that's the number you get. All right. So the average temperature, it's kind of small. Okay, so the average temperature at the room temperature is about 0.03 electron volts. Okay, so maybe it's 1.5. So let's make that 6.2. It's 0.04 electron volts. Okay, so it's 0.04 electron volts. But if you go back to your animation right here, what did we say this thing was? This well depth's around 0.01 electron volts. Okay, so this well depth's around 0.01 electron volts. What would happen if it were collide with an average argon atom at room temperature? Let's say you happen to have this pair of argon atoms. Okay, and then a third argon atom comes by, and on average at room temperature, that argon atom might have a kinetic energy of 0.04 electron volts. So that's going to raise that energy by an amount equal to 0.04 electron volts. So what happens? They're not going to stick together. Those atoms, the pair of atoms that would have been stuck together just by one collision with another argon atom would gain enough energy to be able to separate from each other. That's why at room temperature you don't have any diatomic argon molecules. Okay. So, and like I said, typically once you get to really high temperatures, this well depth right here becomes negligible. So attractive forces at very high temperatures would end up having minimal effect on the behavior of the gas as compared to the ideal gas behavior. You have what's essentially, at very high temperature, this is essentially flat in comparison to the total energy. So you have what's called as in fact, this is what you would call a hard sphere potential. Okay, if you have just a flat potential there and then it just rises drastically at some point, that's your hard sphere model. That's basically dependent only on the intermolecular repulsions. How close can they get before they start to repel? Okay, so the hard sphere model then is a good model to use at very high temperatures because you really don't care much about the behavior and the attractive forces at very high temperatures. Okay. And let's see what happens if you've got a pair of oxygen atoms. That's a very deep well. Okay. Now, if you have a pair of oxygen atoms that are separated to begin with and they're going to collide, they're not going to stick and give you O2. The only way for them to stick and give you O2 is if a third body were to come along and take that energy away from them so that total energy drops down here, then you get your two oxygen atoms to get stuck. And that's how you form O2 molecules. Okay? And if you're dealing with just a pair of oxygen atoms, they're not going to if they were separated to begin with, they're not going to get stuck. You're not going to form O2. But if you have a collection of oxygen atoms, then, a swarm of oxygen atoms, a mole of oxygen atoms, then there's a lot of other atoms there that can take energy away from a pair of oxygen atoms. So you can form O2. Okay, and so you have a very exothermic reaction because ultimately that energy they have to lose in order to form the bond has to go somewhere. So ultimately it becomes kinetic translational energy of the molecules, or it becomes transferred to the walls of your container. Your container will heat up. If somehow you manage to get a collection of oxygen atoms in a container, eventually you'll form O2 molecules and the container will heat up. We say bond formation is an exothermic process. Bond breaking is endothermic. Okay. By the way, let's see what happens here to O2. Let's say I started over here. Oops. That's not what I want. Right there. What do you think is going to happen? Will the two get stuck if I release? Let's see. But what happened? The energy did not remain constant. Energy was not conserved. You should have expected it to oscillate back and forth between these two locations, right? But that didn't happen. That doesn't happen. That doesn't happen in this case because what happens is you have this uh, tendency of excited states to what? Lose energy in by what? How do you excite? Giving off photons. So what you have here, what you have illustrated here is called vibrational relaxation. So in this particular case, it might give off infrared radiation, infrared photons. So you lose vibrational energy, so you go back to the lowest vibrational energy level. Okay. Now, if you did this animation with, you can show the forces involved here. Okay. So attractive and repulsive forces as the atoms move closer to each other and away from each other. So this is what you might see. So if I release that, oops, it's too fast. Slow it down a little bit. See that yellow arrow represents attractive forces, and then your um, purple arrow represents repulsive forces. Electron overlap, that represents the repulsion spark by crowding electrons into a smaller volume. Okay, and there's actually repulsive forces involved there also between the nuclei. But this is just showing you the electron overlap repulsions. This might show better with argon. See? Attractive forces and repulsive forces as the atoms approach as they separate. Okay? Alright, so that's it for real gas.